Welcome to Unit 17, video number 4. This video will focus on the acid dissociation constant, or Ka, and the base dissociation constant, or Kb. By the end of this video, you should be able to write Ka and Kb expressions from acid and base equations. You should be able to relate acid strength and base strength to equilibrium position. And you should understand the relationship between acid and base strength and size of Ka or Kb. Let's start with the acid dissociation constant, or Ka. Recall that strong acids dissociate more than weak acids in solution. We can describe this dissociation by this equation here, where Ha is a stand-in for any acid. Like any other equilibrium system, we can calculate an equilibrium constant. In this case, we're going to call it the Ka because it's for an acid. To write our Ka expression, we're going to take, just like any other equilibrium system, the concentration of the products divided by the concentration of the reactants. Notice in this case we are not including H2O because the concentration of a liquid H2O is constant. Let's practice writing some Ka expressions for some real acids. Looking at number 1 here, our Ka is going to be equal to the concentration of products, H3O plus and HCO3 minus, divided by the concentration of the undissociated acid in the reactants. Again, we do not include water because the concentration of liquids is constant. In the next example, you're asked to first predict the products before writing the Ka expression. In this case, since HF has an H plus to donate, it will act as an acid, yielding H3O plus, the result of H2O gaining an H plus, and F minus, the result of HF losing an H plus. Pause the video here and try writing the Ka expression for this reaction. Welcome back. You should have gotten that the Ka is equal to the concentration of H3O plus times the concentration of F minus divided by the concentration of HF. Now let's talk a little bit about what the Ka value means. So let's take a look at this first example at the top here. Here we see the equilibrium that exists between the undissociated acetic acid and the dissociated acetic acid. Since this is a weak acid, at equilibrium, we have a relatively small concentration of dissociated acid and a relatively large concentration of undissociated acid. This gives us a relatively small numerator and a relatively large denominator. This will result in a small Ka value. In fact, the Ka value for acetic acid is 1.8 times 10 to the negative fifth. This represents a very weak acid because it shows a very small degree of dissociation. Compare this situation to the example of a strong acid at the bottom. Here we have nitric acid, which dissociates almost 100%. At equilibrium, then, we have almost entirely dissociated acid and pretty much no undissociated acid remaining. In fact, we don't even have to draw an equilibrium arrow here because this reaction essentially goes to completion. This will result in a very large numerator and a very small denominator, resulting in a very large Ka value. In fact, the Ka value for nitric acid is actually greater than 10. Looking now at a couple of Ka values for common acids, we see that the higher the Ka value, the more the acid dissociates and the stronger the acid is. In this case, these acids go from strongest, hydrochloric acid, to weakest, carbonic acid, carbonic acid having the smallest Ka value, and therefore dissociating the least and being the weakest of the acids listed. This chart summarizes everything we've said so far about Ka values. Take a minute to jot down this chart in your notes. Pay particular attention to the box that compares the equilibrium H+ concentration with the original HA concentration. Notice this is comparing equilibrium and original. In other words, for a strong acid, the equilibrium H+ concentration will be approximately equal to the original concentration of the acid before any dissociation, because 100% of the acid dissociates. Turning now to the base dissociation constant, or Kb, recall that strong bases have a greater affinity for H+ ions than weak bases. We can represent this affinity through the equilibrium expression down here, where the strength of the base is dependent on the base's ability to grab an H+ from water to produce Hb+ and OH-. Again, we can write an equilibrium expression for this equilibrium system. In this case, we'll end up with the concentration of Hb+, which is the conjugate acid of the original base, times the concentration of OH-, divided by the concentration of base. And of course, all of these concentrations are at equilibrium. Let's practice writing some Kb expressions. For the first example, Kb is going to be equal to the concentration of the products, NH4+, times OH-, divided by the concentration of the reactants, again, not including water. In the second example, again, we're asked to predict the products before writing the Kb expression. In this case, since CO3 2- has no H+ to give, it's going to act as the base and accept an H+ from water to form HCO3- and leave behind OH- from water. Pause the video here and practice writing the Kb expression for this reaction. Welcome back. You should have gotten that the Kb expression is equal to the concentration of HCO3- times the concentration of OH- divided by the concentration of CO3 2-. Let's take a look at what the Kb value means, just as we did with Ka. In this case, we have the weak base, ammonia, or NH3. Since this is a weak base, it will not be able to take too many H+ from water. Therefore, at equilibrium, the concentration of our products will be relatively low, and the concentration of our reactants will be relatively high. This will give us a relatively small numerator and a relatively large denominator, again giving us a relatively small Kb. In fact, the Kb for ammonia is 1.8 times 10 to the -5th, signifying that the forward reaction does not occur to a very large extent. Taking a look at some Kb values for some common bases, we can see, just as with acids, a higher Kb signifies a higher affinity for H+, and therefore a stronger base. Here we have some common bases and Kbs listed, our strongest being hydroxide, and strength decreasing until we get to the fluoride ion, which has the smallest Kb. To summarize what we've seen so far, here's a chart showing the information. Again, this is just like the chart we saw for the acid dissociation constants. Please take a minute to pause this video and copy down this information. This brings us to the end of the Ka and Kb video. Let's quickly review our goals. First, we learned how to write Ka and Kb expressions from acid and base equations, remembering not to include water. Then we related acid strength to equilibrium position, saying that strong acids had an equilibrium position that favored the products, and weak acids had an equilibrium position that favored the reactants. The same can be said for base strength. Strong bases have an equilibrium position that favors the products, and weak bases has an equilibrium position that favors the reactants. And finally, we looked at the relationship between acid and base strength and size of Ka and Kb. Again, large K values signify strong acids and bases due to the equilibrium position being far to the right.